Swayam Prabha. Digital India. Educated India.
Welcome back to week 3 of lecture 3. In this week's lecture more precisely, we are going to study about lump system analysis. So, what do you mean by lump system analysis? Let us consider this tube, our famous our old friend, the one dimensional wave propagation system, where you have waves that propagate in this direction and in this direction. So, what I am trying to say by means of this figure is that you see here there are air molecules everywhere. So, we are basically there is an entire continua, that is what we are assuming, and these air molecules are oscillating about their mean positions. If there is flow, they are also convected. So, the point is that because of this continua of air molecules, we are considering wave propagation in a system with almost infinite degrees of freedom. Although it is a one dimensional system, it has infinite degrees of freedom. So, however, for low frequencies, or if the length of the duct is very small, then it might be considered that the entire particles, all the particles are oscillating with the same phase, or they are behaving like one lumped unit. That is to say, they are no longer a continua, but this entire, suppose you have a duct like this. So, the entire mass in the duct is behaving like one integrated, one common system. All the air molecules can be lumped together, the effect in one system. So, such a special case arises under two circumstances where we have the frequency f is very small, that is f or f naught is very small, low frequency approximation what we call, or talking in terms of a more mathematically elegant manner, or putting it in non-dimensional terms, we have k naught L is much less than 1, where k naught is your wave number. So, let me also, as we go along, let me also recall the units is hertz, that is per second. The unit of k naught is meter to the power minus 1. The unit of L need not be the length, but it could be any characteristic dimension. So, it could be the transverse dimension, that is say cross sectional dimension, or the length, it is some measure of length, it has unit of meter. So, this entire thing k naught L, it is non-dimensional, that is non-dimensional wave number, that is what we call, or non-dimensional wave number, also known as, if you people have heard of it, those who are acquainted with a little bit of acoustics, Helmholtz number. So, the information of frequency is really embedded within this Helmholtz number k naught L. Why? Because this is nothing but 2 pi f by c naught into L. So, this is omega by c naught into L. So, obviously, when f is much small, your k naught L or k naught wave number is also small, but you can also have situations in frequency is very small, very low frequencies 10 hertz, 20 hertz, 50 hertz, less than 100 hertz in general, but length is such that it is large. So, the entire effect will be that a lumped approximation may not be valid. So, if the length or the characteristic dimension is very large and you are yet in the low frequency domain. So, the more fundamental definition is that the Helmholtz number k naught L should be much less than 1. Similarly, you might also have the other scenario where f naught is need not be very small, but the length or the characteristic dimension is very short or very small. So, under those situations also the entire system behaves like a lumped system, like a very short cavity, or something like the length can be considered, this length is much smaller, is very small. Maybe you can actually have things like very flattened out duct, something like this. So, this is the length, this is the diameter. So, L by d is much less than 1. So, well, the idea is when you have such a situation, then how do we go about doing the analysis of such a system. So, that is what we are going to study, spend most of the time in this lecture. So, the thing is, we must also draw, let me introduce something like, simultaneously introduce things like electrical or analogies, electrical analogies or electroacoustic analogies. So, what do I mean by that? So, just like you have voltage in electrical circuits, like this is the voltage and this is, say, your inductance L, or a capacitance C, a resistance R, and this is driven by a voltage, say V naught sine or e j omega t, drives a current, an alternating current. So, the question that I am actually asking is that, can we draw some kind of a parallel with the circuit presented here in acoustics? So, what is the equivalent of voltage V? So, voltage V in electrical circuits, what is the equivalent in acoustics and what is the equivalent in mechanical systems? So, voltage is something like a force, electromotive force that drives the system. So, naturally one would be inclined to think that in mechanical systems V is replaced by the force, say F, V naught, F naught. And what is your force? Force is in acoustics in the context of fluids. So, that is nothing but your pressure into the area. So, in acoustics it is P tilde. So, that is what it is. So, these three things are analogous. Similarly, what is the other thing that we are interested in? So, let me sort of rub this part and let me get some space here. So, similarly, what goes on is the current I, that is the flow of charged particles. So, in electrical systems it is the current I, and in mechanical systems it is the velocity of the body, say V naught, or maybe you should use some different thing, U. Same thing in acoustics. So, here you have obviously force and electrical thing, this is acoustics, acoustic pressure. So, electrical, I will say this as current, and this is mechanical. Similarly, acoustics, we also have particle velocity or volume velocity or mass velocity. The idea is that it should have some sort of a velocity dependence. So, I would say this is, for convenience, I would say this is mass velocity, which is what we discussed as small v. It is nothing but rho naught times the cross section area times u. So, that is what it is. So, there is one-to-one correspondence, and we will also see as we go deep in the discussion how is the inductance L related to the acoustic inductance. What is the corresponding element? Typically, you in electrical circuits you have a what is known as a solenoid, and a current passing through that creates a magnetic field inside it. Similarly, you have capacitance, which is formed by two electrical plates, and there is a vacuum or a dielectric medium placed within that. So, what is the equivalent in acoustics? A resistance, and there are no prizes for guessing. Resistance is exactly equal to damping or the absorptivity in the air, if we can model that. If we do not have damping, you will have perpetual oscillations. So, let us worry about the more important thing which we will consider in acoustics, that inductance or capacitance, because we largely will assume that the medium itself is lossless, unless you of course use a dissipative material in which the physics will change. So, we are not going to discuss that now. Let us talk about inductance L. So, basically what happens is that we are trying to develop some sort of a relation between this thing. So, impedance is defined as force by velocity in mechanical things, or voltage by current, V by I or equal to F by V. So, what happens to the impedance in acoustics? It is nothing but your pressure by mass velocity V. So, let me go to another slide. So, Z equals P tilde V tilde. So, if you have something, a system such as a big cavities or a duct, and you have very short thing, short constriction, this you can consider this as constriction, or a small tube of a small length L whose diameter D is also much smaller than the big diameter between which the tube is sandwiched. So, L is generally small, we will be more precise what do you mean by small, and D by D is much less than 1. It is a short tube connecting two big cavities. So, what happens, like we were discussing just a while back, the entire air molecules inside this duct can be considered as one lump sum or a one particle. So, there are two ways that we will discuss how to go about doing the derivation. One is of course the simpler way, a little bit mathematically more elegant ways to find out the mass, the total pressure that is acting across on the this lumped element, which is nothing but F mass divided by the cross section area, and this entire thing is divided by the mass velocity, which is nothing but rho times S u. So, this then becomes, what is the mass? So, we will worry about that in a bit, rho naught times S square u, okay. And what is force? Mass times particle velocity, time derivative of that, that is mass into d dt of u, Newton's second law, that is what applies here. Mass is not getting changed, you just have this thing. So, we have this square, and remember we are assuming time harmonicity. So, one thing that we will do in muffler acoustics is basically always insist time harmonicity. So, u, which can be a function of both x and t, we can write this as u of x into e j omega t. So, when you differentiate, u dot means with respect to time. So, once you do this thing, you are going to get j omega times x, but x again it is not changing over this length. So, we will just get rid of this u thing. So, j omega. So, the reason we assume harmonicity is because all the IC engine noise that occurs at the first, most of the noise occurs at the first firing frequency and multiples of that, and all machinery they have a certain frequencies of operation, like reciprocating engines, they operate at certain frequencies, and machine tools and so many things. So, for all engineering signals it is advisable that we work in the frequency domain, and it is a standard practice to assume time harmonicity and look at different parts of the spectra, that is a different frequency range, we will analyze the frequency response. So, basically once you substitute this here, so what does it become? Put this thing here and just say Z is m by rho naught S square j omega u by u tilde. So, that is what we are going to get. So, what does it mean then? So, if we do the maths further, we will figure out that this is equal to j omega times m by rho naught S square, and the mass within the element, within the circled element where I have shown it with red color, is nothing but j omega rho naught into S, that is volume, the density into the cross section area into the length L j omega L by S. So, then the impedance of across point 1 and point 2 can be simply written as j omega L by S, where L is the length and S is the cross section area. So, clearly this has the form j omega L inductance, where so this is clearly the effect of sandwiching a small tube of a very short length L, whose cross dimensions or diameter is much smaller than the two flanking cavities. Such a constriction acts like an inertance at low frequencies. Its idea, its basic effect is to act like an inertance, and we will see why it is important in when we will discuss things like Helmholtz resonator. So far we have seen quarter wave resonators, but we will soon see Helmholtz resonator also. You have to wait for a while, and then before actually we begin doing that, there is yet another way in which we can tackle this system. So, we consider, let us say the force is P1, force is P1 here, and at this point it is P2. So, the difference between the force is P1 minus P2. You can consider this as acoustic pressure. So, this is what it is, and cross section area gives you the force that is acting on this element, and using of course Newton's law, it is rho naught times S L. So, that will give you the mass and du dt, mass times acceleration. So, this is nothing but delta p or p tilde, whatever you want to say, rho naught S L j omega u. So, this gets cancelled, delta p by u rho naught L j omega. So, this is particle velocity. So, if we multiply the denominator by S on both sides and of course by density if we divide, so make it mass velocity. So, the difference in the pressure divided by mass velocity, difference in the acoustic pressure by mass velocity is j omega L by S. So, this is yet another way we can derive the inertance of this body. So, this is the role of a inertance. So, what we are going to do is that now we need to analyze the compliance C of a short closed cavity. So, let us consider a tube like this whose length is L, and we will mean precisely what we mean by short. Obviously, intuitively we can say k naught L is much less than 1, cross section area is S. So, if we have a piston that is doing to and fro motion here and here, we will see that your impedance Z at this point is minus j y naught cot k naught L. This is basically in terms of acoustic pressure by mass velocity. So, this we saw from the last few lectures, where we first talked about wave propagation effect, we talked about reflections from one end and so on. So, when we put the impedance condition at the other end, so this is precisely what it is. P by V here, if you measure P and you measure the acoustic velocity, take the ratio of that, so you get the impedance. So, that is there will be your minus j y naught into cot k naught L. So, what happens at low frequencies? This is relatively simple to do. So, cot k naught L is 1 by tan k naught L, and we use the polynomial approximation for tan k naught L, at least in the low frequency. So, this can be approximated in the series k naught L plus 1 by 3 k naught L cube and so on. So, this can further be written as k naught L only when k naught L is much smaller than 1, that is your low frequency approximation. So, you eventually get this sort of a thing, tan k naught L is approximately equal to k naught L. So, once we substitute this approximation here, we will get the denominator to be a simple looking monomial term. Let us do the simplification on the next page. So, P by mass velocity is nothing but minus j y naught k naught by k naught L. So, now this is minus j times C naught S, S is the cross section area as it was made clear, and this is omega by C naught into L. So, this, and you multiply the numerator and the denominator by j. So, you will get just C naught square by j comes in the denominator and S omega L, isn't it? Or do we need to do anything further? Well, it turns out that we probably can do a bit better in terms of mass velocity. So, rho naught into S into u we can write C naught square j S omega L. So, what we are going to do is that S this gets cancelled, and eventually you will have things like impedance that you see here is rho naught goes in the numerator to get us this thing rho naught C naught square, and here you will have j omega L, L is the length. So, the idea is that P by u tilde is rho naught C naught square by j omega L, and now if we were to multiply both sides by S. So, S, so this would of course get us P by volume velocity, P by volume velocity. So, that is your S into u tilde. So, this will become rho naught C naught square by j omega V c, where V c is the volume of the cavity. V c is nothing but S into L, assuming the area is uniform. So, what we essentially get is this thing, the acoustic pressure by your volume velocity, that is your u in times S is equal to rho naught C naught square times j omega V c. So, capacitance, so this clearly has the form 1 pi j omega C, where capacitance C is nothing but your volume V c by rho naught C naught square. And as we know probably that C naught square is nothing but gamma times P naught by rho naught. So, rho naught C naught square is equal to this thing. So, capacitance can be written as V c by gamma times P naught. So, what does this mean is that if we have our ambient pressure, P naught is your ambient pressure, it can be 1 atmosphere, and gamma is your adiabatic constant, V c is the volume of the cavity. So, basically what it means is that pushing a piston into a long cylinder is much easier than pushing into a shorter one, because clearly if the volume V c is less, that means you have a shorter cylinder. So, basically it offers much more impedance compared to a cylinder that is much longer or has a lower volume. So, in other words, capacitance or C part, this thing, this is proportional to the volume. So, the impedance that you see Z is equal to 1 by j omega C, that is inversely proportional to the capacitance. So, naturally if the volume goes up, such a cavity would offer less impedance to the flow of current or to the basically to the acoustic velocity, and a much shorter cavity will impose a much greater impedance. So, typically when we have such a system, so if we, although we will do the Helmholtz resonator in a greater detail as we go, so it is like a mushroom kind of a thing that I am making. So, here you have something like a irregular mass, and here and to the neck of length L is attached, whose cross section area is S, and this can be really, or any arbitrary mass, all we care about is the volume. What is the volume? Vc, it should be much larger than the volume of this neck, and at low frequencies, of course, it has a lumped analysis as we saw now. So, suppose if the wave is coming at this point here, and it is going to see some impedance at this point, and some part will be going in the downward or the downstream direction. So, the question that we are asking is that what is the net impedance seen. So, this clearly this j omega L and 1 divided by j omega c, that will act in series. So, the net impedance is as simple, effective impedance is as simple as adding up the two individual impedances. So, you will get something like this. So, in a sense, so suppose your length is, I would say this as I n, apologies. So, I would say this as j omega L inductance plus 1 divided by j omega c capacitance. So, this is as simple as writing L by S plus 1 by j omega times V c, and here you have gamma times P naught. So, you get this, this is what is you are going to get. So, obviously, there needs to be things like end correction effects and all those kind of things, and we can simplify this thing further to find out the precise frequencies where the impedance will tend to 0. All those detailed analysis, even a better approximation of the Helmholtz resonator or of a short cavity, that we will consider in the next lecture, where we will first discuss about the end correction effects and how does it happen, and then probably develop an even better expression for a short end cavity by considering a higher order term and relating both things together, and then probably going into more complicated elements as we discuss more about electroacoustic circuits. So, that is all for this lecture. Thanks a lot.